Yesterday, the two classes of algorithms that we discussed were, on the one hand, sampling kinds of algorithms. In particular, I did an example of this cloning type algorithm where you are copying those instances of your system that do what you want, and you are throwing away those that don't. You kind of get an effective bias, and you need to correct for that bias after the fact. This is one instance of a method in the larger class of importance sampling algorithms, and I wanted to develop a bit today Monte Carlo type algorithms, what is their problem with their events, and then how to implement an importance sampling Monte Carlo. So this would be lecture 2 now. Sampling and biasing. What we dealt with yesterday as an example are extreme events that come from the solution of random processes, maybe more concretely of stochastic differential equations. So we consider some kind of stochastic differential equation for some random variable x that is maybe in Rd. So d degrees of freedom of your system, d can be very large. So this includes maybe this ship example where d was 2, but it also includes maybe a climate simulation where d can be 1,000,000, where you have so many degrees of freedom. And then your differential equations might look like something like this. I'm just writing this down because this is the generic form that I will be dealing with both today and on Thursday, where I'm saying I have a deterministic drift term B that maps, is basically a vector field that maps from Rd back to Rd. That gives me what the system does deterministically, and then I have a noise term. I choose to just choose white and time Gaussian noise. Maybe you would have like a different covariance. A physicist would maybe write this is the same as x dot equals p of x plus eta, where eta is some noise. So maybe with some covariance where we say eta prime is correlated as white and time, and some correlation for the other degrees of freedom, ij. These specifics don't matter too much, but instead, what we want to focus on is we are interested in what I would call extreme events and their likelihood. So maybe given a function f from our configuration space Rd into the reals, maybe you would call that the observable. We are interested in the probability of our observable maybe at the final time to exceed the threshold z. So we have a process, maybe that is simulating the climate on Earth. We have some function, maybe this is the mean temperature in France, that maps to the reals, it's a number. And then we want to compute the probability that at some final time, maybe in a month or so, that the temperature in France is bigger than some threshold. And if z is large, this will be a range. So I will often call that p of z, or maybe p of z comma epsilon, because usually, and the systems are designed in such a way, the bigger z, the more extreme the event. The smaller epsilon, the smaller is the noise, and if the event is atypical, also the more rare it is. And exactly that dependence on z and on epsilon, we will look at in more detail for very simple processes. Hopefully also on the computer, but it also stopped working already. So that's the generic setup. Another instructive way of looking at that, I'm just introducing notation. Sorry. Instead, I can look at this as a set. Az is all those x in my configuration space for which f of x exceeds my threshold. So if we stick with this climate example, this would be all configurations of Earth where there is a heat wave in France. So these are basically all those events that are extreme. And if that's the case, then I can say that this probability is the same as the expectation of the indicator function of this set at the final time, where with indicator function of the set, I simply mean the function that is either 1 or 0. It is 1 if f of x is bigger or equal z, and 0 otherwise. So if you have not seen that function, this basically identifies the set, AZ itself. Z is the set that scales depending on how extreme is our event. And this probability then becomes simply an expectation of that function, which simply means, well, it's 1 whenever we do exceed the threshold, is 0 otherwise, and probabilistically we then will then see how often this happens or doesn't. So once you've established that, we can write down in more detail what we played around with yesterday, which was this coin toss example, which leads to the first and maybe most naive implementation of a method, the so-called Monte Carlo method, the naive Monte Carlo method, if you will, in this context. For this one, we have m independent realizations of our SDE. So maybe I write the Monte Carlo index here, something like that. So each of these, maybe from 0 to t, I didn't specify what that implied here. But t maybe is starting at 0 and ending at capital T. So I have n independent realizations xi. Each of them is full simulation of my system. And then I say my Monte Carlo estimator, which also I want to parameterize depending on how extreme is the event and how small is the noise, is simply then the average of the indicator function. So all I'm saying here is that I do capital M independent simulations, and I count them as 1 if my rare event happened, I count them as 0 if it doesn't, and I compute the mean. So this is just tossing the coin and counting heads or counting tails, and then just averaging how often does it happen. So in this sense, this describes both an algorithm, what I need to do, but it is also a random variable itself, because all of these are random realizations. I average over them, so this has a random outcome. It doesn't have a specified deterministic outcome, but whenever I do my Monte Carlo experiment with M realizations, this average will approximate the true one, but it's not equal to the true one in general. One thing to note, though, maybe that's completely trivial, but I will write it down anyway. In expectation, of course, the estimator is correct. So the expectation of the estimator gives 1 over m, the sum of the expectation of the indicator function for each of the xi. And this one we know is equal to pz. So each of these give me a pz. So it's 1 over m sum over I, which goes to m of our rare event probability, and this is just this m times, so 1 over m and the m cancel. So this is exactly p of z. So all I'm doing here is saying, in expectation, our naive Monte Carlo sampler gives the right result, which is maybe what you expect. Good. So to give a concrete example of that, I want to look at Brownian motion. This is the simplest example of the SDE of the previous form, because this just sets b equal to 0. So it's a rescale Brownian motion if you want. I'm just saying dx the square root of epsilon dw. I want to start at 0, and my time is between 0 and capital T. So if we define every single quantity, my observable is simply the variable itself because x is in the reals. So I say into 1 maybe. And then our event simply becomes the probability that our random walk at final time exceeds some threshold z. And this is again can be written as the expectation of the indicator. So this example is simple enough that we can compute the answer precisely, just because we know that x at the final time will be distributed according to some probability density function rho, where rho of x is given by a known function, completely like properly normalized to pi epsilon t and then e to the minus z squared. So x squared. So maybe you know that, maybe you don't, but it's just a random walk. That means the Fokker-Planck equation just means it's like a Gaussian curve. Your Fokker-Planck equation is a heat equation, so you get like a Gaussian curve that spreads over time. So the width of this bell curve increases with time. So because we have that result, so I need to hide it again. Yeah. We know that the final probability is simply the integral starting from z, which is the point that we want to reach to infinity, because these are all possibilities of exceeding the threshold z, of rho of x dx. And for this Gaussian curve, this function has a name, not that it's important, but that's like the, I guess, cumulative error function. I'm just writing this down because there is an exact result and we want to compare against it. So this is the exact answer of what's the probability of exceeding z at time t for this process. It's the integral of a Gaussian distribution or a normal distribution. How would the naive Monte Carlo look like for that? It integrates m copies of the equation and then estimates according to the usual mean. So 1 over m from I to n of the indicator function of the ith realization at final time. This is a simple function now. This is just one if xt is bigger than z. Right? None of this is somehow secret. So now I hope that I can get my laptop to run because I wanted to demonstrate exactly that. Doesn't even say no signal. There you go. So I wanted to implement something along these lines.
of integrating this equation up to some final time t. So maybe I define myself a number of time steps, 1,000, a time step 0.1, an epsilon also 0.1, a z maybe 10. We'll see if I forgot something. And then I say x, which is my variable, starts at 0, and I just integrate steps from 1 to nt, and I do a simple, let's call it naive. Yes. X, the new x is the old x plus delta t times the drift, but that's 0, plus my noise. So that's just a normally distributed increment of the size of x. And I mean, I'm not particularly teaching how to implement this, but if we would want to implement a forward Euler scheme, the noise must scale like square root of dt. So this would be an integrator of the Brownian motion. I have a random noise that has variance 1, but the actual variance that it should have should, of course, contain the square root of epsilon, because that's what I wrote, and the square root of dt, because that's the proper scaling of maybe the delta function that is the white-hand time for variance. So I probably did something wrong, but maybe let me try. Naive, so I have now an x. Yeah, so that's one realization at time t. So because I want to do many experiments, I have an m. Maybe we do 1,000. Maybe first we look at the trajectory. So maybe we say the x's are nt times 1 zeros, and then every time step I say s in entry becomes x. So this should, if I run it, then I have the whole trajectory, so I can plot it. First time plotting something takes a while, I guess. Not the x, I want to plot the x's. Yeah, so this looks like a realization of this thing. Whenever I run the naive sampler, I get a new trajectory, right? It always starts at 0 and it ends somewhere. And now I want to do this experiment m times. So that's what I did earlier. M equals 1,000 maybe. And then it's not a 0, so I'm integrating m trajectories at the same time. This is a vector with m entries. This is a vector with nt times m entries. The rest should survive, I guess. So if I do it again, 1,000 trajectories, you plot them immediately. This is 1,000 lines. So how many of them are bigger than 0? Maybe if we plot the x-axis in blue, and then we plot those x-axis. Now I need to think all times, but only those trajectories which exceed z in red. Well, there are none that are bigger than 10, I suppose. So 10 was maybe a bit high. But if we would have z equals to 6, then this bit of them would exceed 6. So all of them are the ones that end up somewhere higher than 6. So if we now want to implement our sampler, z should be equal to, well, those that are bigger than z. We could actually write it like that. All of that are at the end bigger than z, right? Mean meaning just the sum and then divide by the number of entries. That's exactly what I wrote here. And x bigger than z is a function that's either 0 or 1, depending on whether we are bigger than z. So I wanted to compare that against the exact one, which I wrote down as a half, and then the cumulative error function of z over square root of 2 times epsilon times t. T is dt times nt. So we can try. And you see that pz, because I only do 1,000 trials, is mostly either 0 or 1, while the exact answer is somewhere between, sorry, not 1, but 10 to the minus 3, while the exact answer is somewhere between that. It's a bit smaller than 10 to the minus 3, it's 7 times 10 to the minus 4. So if we did maybe a few more experiments here, maybe 5,000, that would wait too long, then we get closer to the result. So we said the sampler says 6 times 10 to the minus 4. The exact result is 7.8 times 10 to the minus 4. But we have some variance in the answer. So I hope that all of you somewhat understand this pseudocode. I'm just using MATLAB because then I can immediately show and plot, but you can use Python or some Python notebook or whatever. But all that we are doing here is repeatedly integrating the differential equation. In this case, I do it all of them at the same time, because why not? 5,000 differential equations at the same time for 1,000 time steps, and then I just look at the results. So we saw that while we can get an answer that has at least the correct order of magnitude, there is a somewhat high variance to the whole thing. And that's what I want to discuss next, how this can be specified, this problem. And this is summarized under the term of the relative error of a sampler, of an estimator. The first thing to ask is what the variance of an estimator. So this, I hope you have heard of. The variance of a random variable, maybe in this case of our Monte Carlo estimator, is simply the expected deviation from the mean, if you want. So the expectation of the difference between the expectation and the actually observed one squared. Square, maybe I do like that. So this is the estimator itself. This is its expectation. On average, they are the same, but there is a difference, and if I square it, I somehow cancel the sign and the expectation of that. But you can rewrite this easily, you've probably seen that, as the expectation of eta squared minus the expectation of eta squared outside. So we know that the expectation of eta is going to be p of z, but the expectation of eta squared is something different. Now I need to erase. So I now want to demonstrate why this is a problem for us. I define, looks more fancy than this will be the only definition, I guess. The relative error of an estimator or E is the ratio of the square root of this variance divided by the expectation. So this is always again z epsilon. So the square root of the variance is also called the standard deviation, I guess. Doesn't matter how you write it. The point is that the square root of the variance or the standard deviation is intuitively the amounts of fluctuations that you expect for your random variable, in this case for your estimator. The bottom is the mean value of the estimator. So this is basically normalizing the fluctuations with the mean value. If the error would be 1, this means that we have fluctuations that are roughly 100% of the mean value itself, right? If the probability is, I don't know, 0.5, and the standard deviation is also 0.5, this means that the error would be 1. Meaning also that basically the error is as big as the variable itself. The relative error is much more meaningful than the standard deviation itself in this context, because it needs to be normalized properly by the mean value in order to somehow have the right units, if you want, right? So you don't care about how your absolute fluctuations are, you care how big your fluctuations are relative to the measurement of the value that you have inside. This is why it's called relative error, because it's relative to the expected value. So a value around 1 might mean that our errors are on the order of 100%, which sounds bad, but we can do much worse.
and I often do. And something that's smaller is obviously better, and something that's bigger is obviously worse. So let's take, for example, a random variable that's distributed according to the norm density. So I leave a bit now the setup where I'm using SDEs, but for the Brownian motion, we of course know exactly that. For the result of the SDE at final time, it has a non-distribution, which was this Gauss normal distribution. Then the probability of observing some of these rare events, so just to define it, is again that my random variable exceeds z, can again be written as the integral from z to infinity of rho x dx. So that my estimator for that, for this problem, which simply is 1 over m, the sum from 1 to m of the indicator function, the ith copy of my random variable, right? And each xi is drawn from this distribution in this example. So I've already convinced you, hopefully, that on average, this estimator gives pz itself. So in order to compute the relative error of the naive Monte Carlo sampler, the only thing that remains to be computed is its variance. And that's the thing that I want to return now. So what's the variance of the naive Monte Carlo sampler for this problem? It's the expectation of eta of z squared minus the expectation of eta itself, and all of that squared. This term is clear because this is just pz squared. This term we need to work with it. So eta of z I will just insert. Each of these etas is a sum itself. So if I have eta times eta, it's a double sum. So it's the expectation of 1 over m squared, and then the sum of I and j from 1 to m. And then we get an indicator function IAZ of the ith realization, and an indicator function of the jth realization. And then take the expectation. All of that minus pz squared. Because that's just the expectation of z. So the two cases that I need to distinguish for the double sum, because each of these xi or xj are independent draws of my random variable. So if I is equal to j, of course they are not independent because they are the same draw. If this indicator function triggers to be 1, then this one would as well, if I is equal to j. The other case, if I is not equal to j, they are independent, so the expectation of their product is the product of their expectations. That's just it there. So I can basically get two terms. This is just continued from there. 1 over m squared. And then I have the sum of I equal to j. It's a weird way of writing it. It's just the sum over I, but I want to split it in I equal j and I not equal to j. Of the expectation of the indicator function at xi, and again, but the indicator function squared is again the indicator function, right? Plus the sum over all I that are not j. So you can think of that as the sum over an array of size m by n. This would be the main diagonal, this would be every other entry. So here the two are independent, so I can write the expectation individually. An xi and another expectation. Is that clear so far? Or? So this, as I said, is maybe some main diagonal of a square domain. These are m terms. Each of these terms, because the indicator function squared is the same as the indicator function itself, is pz. So this gives me 1 over m squared and then m times p of z. This one is pz squared. Because it's pz and another p of z. How many terms is it? It's m squared terms minus the diagonal terms, so it's m squared minus m terms. Now we just need to collect. There's a 1 over m squared but times m. There's a 1 over m squared times p of z, which is just p of z squared. And we subtract it again, so this term cancels this term. And what remains is 1 over m p of z minus p of z squared. One over m p of z 1 minus p of z. Maybe you've all done this calculation if you had a probability class. It's just like, I guess, the variance of the binomial distribution. Particularly to our case, if pz is very small, this is approximately 1 over m p of z, because p of z is small against 1. This term is basically. So therefore, the error, which was this variance divided by the mean, and the mean is p of z, sorry, it's the square of this variance divided by the mean, is just 1 over square root m, and then square root p over p, so it's also 1 over square root p. So, fine, this doesn't look too problematic. I mean, one thing to note is, of course, the more samples you have, the smaller is your error. You need to square the numbers of samples in order to linearly decrease the error, but that's not uncommon and maybe even expected. But the smaller the probability, the bigger the error. This is exactly this thing that we are encountering here. And maybe even worse, for the example of Brownian motion, I already derived p of z epsilon. So in this case, we have an epsilon again. I skipped it here because this was just a random variable. There was no epsilon, that's it. But here we have these two variables. It was this. So it was this weird error function that maybe I just wrote it down in order to be able to implement it. But the limits of this error function are known. If I let z to infinity or epsilon to 0, which amounts to roughly the same, I mean epsilon squared scales like z, this has a known limit and it looks like the normal distribution itself. So this converges to, in the limit, something like minus z squared over epsilon. Yeah. So the tail probability, if you want, decays exponentially, where in the exponent you have z squared, the size of the event itself, and epsilon, the size of the fluctuation. This is maybe not at all surprising. The curve itself is the Gaussian to the tail scales like. But why is this particular bad in this case? I can insert this p of z epsilon here to get the estimator of this thing, right? This is exactly what we implemented.
So somebody copying that. Since we have this below scaling of P of Z, the relative error of our estimator for low probabilities, which we said was something like 1 over square root m, and then 1 over square root P of Z epsilon, is something like 1 over square root m, and then P of Z was e to the minus z squared, so this will be e to the plus z squared over 2 epsilon. The 2 comes from the square. So what you see here is not only that the error is big, but that the error, the relative error, exponentially blows up with the extremeness of the event or with the smallness of the noise. So very concretely, if I want to have a certain error guarantee or a certain error bound, maybe one, I don't know, the number of samples that you need to look at needs to exponentially scale with the rareness of the event. So I need exponentially more samples if I increase epsilon by a linear factor, or if I increase z by if I decrease epsilon by z. So this is the bad news in more concrete terms. So yesterday we just juggled with the coins and yeah, it looked bad. This is how bad it really is. It's exponentially bad. And I guess this is a reoccurring story in these extreme events, that tail events often are exponential. And if the probabilities are low, your variance is easily blow up.
That's already for normally distributed.
This is for normally distributed, but this exponential scaling you get for a large class of systems beyond just.
Yeah.
I mean, on Thursday,
For catastrophical phase transitions, it might not be valid. I mean, some systems have tipping points where it's not or are they also approaching normal distributed systems?
So I don't claim that this has anything to do with normally distributed. This has only to do with the tail scaling exponentially.
Okay.
Right? Which is the case for normally distributed, but this is true much more generally.
I think yes, that I agree.
Yeah. So here I can just compute it explicitly for the Brownian motion and for normally distributed, but yeah, the bad message prevails a lot. Not always, of course, but a lot. Yeah, you have to.
Yeah, I was wondering, just to image, I mean, you have now a normal distribution, and Monte Carlo, I mean, it's like a uniform sampling. And of course, if you look at the tails, the fluctuations will be very big.
Yes, this is all that I wrote down.
Yeah, that's actually what the interpretation, right?
Yeah.
But if you have an extreme value distribution with a P, I mean, I don't know how those things are, free share or whatever. Then you have much more, the tail is much larger, so you have more.
Yes.
Observations there, and if you do it then uniformly, really, I wonder whether it still holds.
Yes, the problem is less bad in that case. It all depends on how likely these events are.
That was the case.
So it seems that I call uniform Monte Carlo, and if Monte Carlo doesn't work for Brownian for norm, but it seems to work for extreme value distributions.
So the generally true thing is that you have a 1 over square root of the probability, right?
Yeah.
If your probability diminishes, then your error increases. Yeah. But if the probability decreases only linearly in whatever you are considering, you are usually good. Yes, it's true.
Yeah. So even naive method is better for an extreme value.
No, you will never have that the tails are more likely than the typical case. The probability in the tails must decrease, otherwise you wouldn't call it a tail, right? Yeah. It must always go down. So your error will always go up. But here we are talking about something much worse, right? Not that it goes up, that it goes up exponentially. That's much worse than what you are talking about. So there are distributions that have a much milder decay, and then maybe you're. That is true. Yeah. So this is why I wrote it with this epsilon and STEs, because there it's always the case that it's exponentially bad. Because you always have some kind of large deviation principle, which will come on Thursday, where you have provably a tail decay that's exponential. It need not be z squared, but it will be 1 over epsilon. And that's the problem there. So the last thing that I want to do, and then maybe we can take a short break, is to basically measure the relative error of this thing. I just want to do this because obviously we will later want to improve on it and implement a better thing. So maybe I call this relative error. So I do a number of experiments, maybe 100, just to get the variance. And every time I call this naive thing, and I have an array for the answers, PZs. So this naive that I implemented gives me a PZ. And then I say all the PZs are all the old PZs, and then I add the new PZs to the list. That sounds maybe reasonable. What do I call it? Relative error. So you see that I now do 100 times this experiment. It flickers between 0 and 10 to the minus 3 because these are the values that I take. But I now have this array of answers. If you look at how this looks like, I sometimes have the outcome of 0. I sometimes have 1, 10 to the minus 3, 2 times 10 to the minus 3, sometimes 3, sometimes even 4. So this, I guess, corresponds to observing the event 0 times, 1 twice, 3 times, or 4 times. These are the options that I have. And that's why the variance is so high. So if you look at the variance, it's some value. So the quantity that we want to look at is the standard deviation of the measurements divided by the mean. And the relative error is of the order 1. By the way, the mean itself should be closer to the exact one, right? And it hopefully is. Yeah, so it's not as bad as the individual ones. Oh no. I guess we need to live with it until the break. So we can now play around with this a bit. So the relative error I said is the standard deviation divided by the mean. So whenever I do this relative error experiment, I get a relative error that's roughly 1. Maybe I should suppress the output here. So if I would make the event more likely, maybe we don't want to exceed 10, but only 5, the relative error should be smaller. And if we make the event less likely, maybe instead of 0.1, we do 0.09. It's a bit hard to measure the relative error itself because I'm only doing 100 samples to measure the relative error. So it blew up from 1 to 1.8. So I go from 0.09 to 0.08. It goes up even further. So now the relative error is already order of magnitude 2 or 3. And this is exactly what we are dealing with here, that the epsilon equals 0.1 or 0.08 is not that much of a difference, but the relative error very quickly blows up. And in 0.07, probably we can't get much further. It's the highest relative error that I can measure with 100 trials is 10, I think. So it increases exponentially, both with the noise becoming smaller and smaller and the amplitude becoming bigger and bigger. And maybe this is a good spot. I mean, I basically just outlined the problem and I didn't demonstrate any kind of solution, but hopefully we can get to that in a second. Yeah, see you in, we said 15 minutes last time, so maybe see you at 11. Let's talk again after the break. I hope it was possible to follow for you, or maybe you knew all of this all along because it was basically just Poisson statistics. Maybe applies a bit to these kinds of problems that we are interested in, namely integrating larger scale stochastic differential equations. But at the moment, there was not much coming out of the SDEs, except that it gives you a distribution of your final configuration, and then you have some observables on that. In any case, the outcome that we observe, for example, for the Brownian motion, more generally for any kinds of SDEs of that form, is that if you have a rare event, oftentimes the probability tail scaling is exponential, and that also means that your relative error will blow up exponentially with the extremeness of the event or with the rareness of the event, where maybe you could call Z how extreme your event is and epsilon how rare your event is. But of course, making it more extreme makes it also more rare, and making it more rare makes it more extreme in relation. So
all of what I did was basically just highlighting the problem, as I said. And now I want to start off with the first kind of sampling algorithm that solves this problem to a degree. And this is importance sampling. So I'm going to introduce it for a simple problem. So simple that maybe you will laugh and say, I mean, it's stupid that this works. Then when we apply it to STEs, it's going to be a bit more complicated, but hopefully we will get around to implementing it in the same way that I did for the Brownian motion. So the idea of importance sampling is we want to sample from a completely different distribution than the one that we started with. Namely one that makes the event less rare, maybe more typical. Because then we get better statistics on them, which decreases our variance. Of course, sampling from a different distribution means that you're solving a different problem, not the question you're asking in the first place. So what you need to do is you need to correct for that change. Correct for that change in distribution. So the simple example that I wanted to compute is, we had it before, a P of Z. That was the probability of our random variable exceeding Z. That's the integral from 0 to infinity of our rho of x dx. If I'm saying x is distributed according to rho. So rho is the probability density function of a random variable x that lives in the reals, maybe, because these are just 1D integrals. Otherwise, I would need to integrate over Eta. And the thing that I'm going to do now is to say, assume I have a different random variable. I call it y, and it should be distributed according to a different probability distribution, theta of y. So this is the way we look at theta. What I said before, P of Z is integral from Z to infinity of rho of x. The only thing that I'm now going to do is to say, well, I can write this as rho of x divided by theta of x dx. I just divide it by theta and multiply it again by theta. But similarly to how this was an integral over a density, I can now interpret theta as my density. So this is basically saying this is the same as an expectation, but now according to my new distribution theta of the indicator function of my y. But I need to multiply with a factor, rho of y over theta of y. Obviously, it only works if theta is non-zero wherever rho is non-zero, and a probabilist, I guess, would call then theta to be absolutely continuous with respect to rho, and this is some kind of change of measure, or rather Nikodym derivative. But here it's simply just division in the simplest case that I'm talking about. So before I said P of Z is sampling over the distribution rho, the indicator function. Now I'm saying I can instead sample from variables distributed according to theta, the indicator function, but I need to correct for that. And the only correction that happens is the relative likelihood between the two distributions. It's really nothing but dividing by theta and then multiplying by theta and reinterpreting the integral. So this is some kind of reweighting. HT. And maybe I call Z of y, my rho of y over theta of y, the reweighting factor. So in this manner, I can translate between any probability distribution to any other probability distribution as long as the ratio makes sense. And therefore, I can construct a new sampler, Eta importance sampling, which is instead just saying I average not over my initial distribution, but over any other distribution. Everything is allowed. So these will be the indicator function of z now evaluated at yi, where with y I mean a random variable distributed according to a different distribution, but multiplied with z evaluated at y. So this will give the same original pz, but I'm free to sample from a completely different distribution. For example, I could sample from one distribution that is somehow localized in the tail of my original distribution. These z's would be small then, because the relative likelihood has this smallest factor. Basically meaning I'm drawing from something that is occurring in the tails, but I correct for it because I know how unlikely the tails are in relation to my original one. Sorry, how much more likely the tail is corresponding to the in relation to the original one. So it's basically still computing a mean, but each copy doesn't count for a factor 1 or a factor 1 over m if you do that, but for maybe a lower or bigger factor. I prefer different values, but I correct for it. So of course we still have that in expectation this sampler is still P of z. It's the same as an 8. So this is important sampling, and as I said, at this point it maybe looks trivial or even like puzzling. How could this work or how could this make a difference? One thing I want to highlight is what it does to the relative error, because this sampler is still easy enough that we can compute this through. So what's the relative error of the importance sampling estimator? I'm just erasing the relative error thing and I'm going to rewrite it again, but it's now for different samples. So the expectation is of course still P of z, but what's the variance? That's what I need to compute. So the variance of eta is. So this is the expectation of the importance sampling estimator squared minus its expectation squared. So similar to before, so this is expectations according to theta, keep in mind, right? Is the expectation of 1 over m squared, and then the double sum again. So ij, and what I have inside here is the indicator function at yi, but also z at yi, and then the indicator function at yj, and also z at yj. Then I will split out the double sum between the diagonal elements and the non-diagonal elements, because either in the diagonal case, these two are the same thing, so I can reduce them to only one indicator function. In the other case, they are independent, so they can be multiplied out. This will be I equal to j, yi squared, I guess, just the same as the indicator function itself, and then z squared. And then plus the sum where they are not equal. Where is my expectation sum? Here they are independent, so I can say this is the indicator function at yi, and then z at yi times the indicator function at yj times z at yj. each of these are P of Z again. But here it's a bit more awkward. So the number of terms is the same as before. These are m terms, these are m squared minus m terms. So m times. And now this expectation according to theta, but with the weight z of the indicator function, where the square can just be erased because the indicator function squared is indicator function, can be reinterpreted according to the original distribution rho. Because the original distribution rho is the new distribution times one of the z's. So this is basically the expectation of the indicator function at an x times one of the z's. So I transform back from y to x. This is now according to rho. But this is not P of z, this is something that's reweighted. And the square is gone because one of the z's is absorbed into the original theta. And I replace the i's with an x to say this is the other random variable, but also I no longer sum over anything because all of them are independent. So I can just replace it with the original expectation, m times. While this one is just again m squared minus m times P of z squared. So yet again, this term cancels this one, and I arrive at the 1 over m. And now the expectation is going to be x random variable of indicator at x times z of x minus p squared, right? This one.
So 1 over m squared, right?
No, this is an m times and then divided by m squared. So it's 1 over m and that's outside here, right?
Oh, yeah, sorry. Yes, sorry.
So I don't think I can simplify any further. That's just the answer. And it's a bit of a disappointing answer because we can't really say without knowing the z. But maybe that is expected in that the variance depends, of course, on the change of variables. So the important sampling relative error is given by something like 1 over square root m. This scaling is unchanged. That's maybe expected. And then I need to divide by p because that's also p, right? So I get something like the expectation of the indicator function, but times the z divided by p of z squared minus 1 to the 1/2. So far, I think this is maybe not too helpful. That's just the formula. And I guess if you give me a change of measure from one to the other, meaning you give me the z, I can compute the relative error that you would expect to have. But there is one crucial point that's interesting to note. It is the following. Consider this change of measure. Consider z star this one. If I insert this change of measure into this z, the one I z will just be the same here. I get a p of z that I can draw out, and I get an expectation of 1 of z, which is another p. So to just write down what I'm saying, the expectation of this times the z star is the same as p of z times the expectation of the indicator function. It's the same as p of z squared. So that's another P of Z. P of Z squared divided by P of Z squared is 1, minus 1 is 0. So for this particular change of measure, the relative error is equal to 0. There is a choice of a change of measure that not only has a very small relative error, it has a 0 relative error. It's a 0 variance estimate. This seems somehow magic, or it seems like cheating, right? I can change to a measure, if I make my change optimal, but I don't need to perform a million estimates. A single estimate is enough because every answer will be the same and it will be the correct. There is no variance anymore. There is only the right answer. That feels like, okay, we should always use that, but of course there is a caveat, namely Z star includes P of Z, which is the quantity that we want to estimate in the first place, which we don't have, right? P of Z is the outcome that we are interested in. Of course, somehow if you plug it in, you can get it out again with 0 variance. This is basically just saying, I change to the measure that's exactly tuned in a way that it will always give me the right event, but weighed according to the probability of that event. Still, it's good to know that there is an optimal change of measure, or there is an optimal importance sampling algorithm, which is usually inaccessible, but maybe you can write it down in theory. Because if you don't hit the optimal one, but something that's slightly worse, you might still approach a 0 variance estimator approximately. So a lot of practical importance sampling schemes do try to estimate this one in smart ways. For example, you can consider a measure, an estimator, that on the first go estimates P of Z, and then inserts it here somehow in order to get a better change of measure to estimate P of Z better, and then do this somewhat recursive. Something of that form. Or you could imagine that while you don't know exactly P of Z and these kind of things, you have maybe a heuristic that's quite good, and this you can use as Z star again. In short, though, any change of measure, as long as it fulfills certain restrictions like this fraction being well defined, is valid. And you can just try and look and measure the relative error and decide whether it's good or not. So empirically, you could also try to get it. So maybe to write down the conclusion, this is a 0 variance estimator, which is maybe paradoxical. But it needs P of Z, which is what we set out to get in the first place. So that's great and all. And it's quite simple, but what I now wanted to show is how does the same thing look like for sample paths, for prop STEs. And this will be the first time that it actually matters that we are doing STEs. The change of measure from one random variable to another is easy, it's just like this ratio. But the change of measure from one path measure to another is a different beast mathematically. So in this sense, I will only basically write down the results, which are well known. But I mean, I won't derive it or go into any more detail. I guess if you're interested in it, you can look it up. It's more or less standard stochastic analysis. But I just want to use the result in order to then go on and look. So maybe I erase this one because it's so much easier to write. So this is now importance sampling for sample paths. And it's going to be a bit unfair because I'm just throwing terms at you now with much less background because the background would be a bit bigger and not really fitted to, I guess, 2 hours before. So how does the same look for sample paths. So in general, you can always say for generic probability measures, for generic measures if you want, in the mathematical sense, or the measure theoretical sense, the probability of some event omega is the integral over this omega d mu. This is how you would write it. It's just d mu by d mu, where this is called the Radon-Nikodym derivative. Which I guess generalizes the notion of derivative from functions to measures. And concretely, how this term looks like for sample path is well known. And this is covered by the so-called Girzanov theorem. I don't know how to pronounce it actually, or where to stress it. So for path measures, exactly what it is. This is covered right here. So this is the result that I want to state. And while maybe the proof is out of reach, I still think that it makes sense to state the result itself, because this we can immediately use in order to build an estimator for estimates. So the theorem goes as follows. Here's enough. So we have xt being the sample path distributed according to a measure that I will call P, maybe P index X, which is just meant to be something like a density, but not acting on the reals, but acting on whole trajectories of my SDE. So let xt be samples distributed according to a path measure P of X. Solutions of, and then our original SDE. And YT sample paths distributed according to some path measure Q, solution of a different differential equation. YT is now C of Y. So the only thing I'm saying is that I have my original SDE, and if I generate paths with it, for example, with my code, they are distributed somehow, and I call this somehow P. Now consider a different SDE where the drift is different. The noise must be the same. The drift is different, and I call paths drawn from this SDE as if they were drawn from a sample path measure Q. And now I want to quantify what's the scalar factor of changing from one to the other. So in order to do that, I say I define a new variable u, but properly rescaled, u of x, to be b of x minus c of x. And I demand an expectation u squared of fds bounded. This is called the Novikov condition. That basically a u that's the properly rescaled difference between the two drifts, and it fulfills some exponential bounds. maybe the then of the theorem goes here. Then dq is equal to e to the minus integral from 0 to t u of ys ds, sorry, dws, minus 1/2 integral from 0 to t u squared of ys ds. dp. So maybe not entirely clear what all of that means, but in principle what I'm saying is there is a factor that's e to the integral of this difference in the drift term, and also so this is a stochastic integral and this is a normal Riemann integral of u squared, that gives me the translation factor between solutions of this SDE to solutions of that SDE. Because what I'm interested in the end is this dq by dp, mu by dnu, in order to say, before what I did was integrating this SDE and then evaluating it according to the P1. Now I want to evaluate it according to the Q1, so I need to multiply it with a factor, and that's the factor. But this is completely accessible numerically because if I'm drawing samples from the new SDE, then I can just compute this factor. That will usually be a small number that I need to multiply against it in order to allow me to sample from the other. So maybe we have now reached a state that you haven't seen that before, but I think it's still doable to exactly compute this factor numerically. And that's maybe the last thing that we are attempting to do. But a concrete thing to note here is that we again have this notion of the optimal chain of measure. So there is still an optimal, I call it tilt, because in effect, this u, which is the difference between the B and the C, is somehow how I tilt my whole SDE towards a certain outcome, right? The u is, instead of using my original drift B, I want to use a certain different drift C in order to push it towards a certain rare event. So u is kind of like tilting the whole system towards a certain direction to make it more likely. I define a function psi of xt to be the expectation of a process starting at time t at point x of exactly hitting my ray event at the end. So this is a similar spirit than the thing that we just did for real random variables, just for paths. I need to have a function that gives me the likelihood of realizing the ray event starting anywhere, at any time, at any point. If I had that, so I guess where with this symbol, I mean it's the expectation of this equation. We already had equation 1, so this is equation 2, I guess. But starting at time t at point x. Then the optimal still, u star of x and t, is minus square root of epsilon. I just drag this epsilon along, the gradient of the log of psi. If I were able to compute this psi, plugging it in here and getting a u star, this would give me a change of measure that would result again in a zero variance estimate. I can instead integrate an STE that always realizes my ray event and is reweighted accordingly to compute the exact probability of that ray event at the same time. So the proof of that is not too difficult if you've seen Feynman-Patz formula, but of course, maybe it's not realistic to do that here. But what we can do is to compute this optimal tilt for the Brownian motion. Just because we did Brownian motion all the time, And it's easily doable, and then you will see how the optimal tilt actually looks like if you integrate. So example, Brownian motion. Well, the Brownian motion, the B was 0. That's the special case of the Brownian motion. But we also know this one. What's the likelihood starting at x and t to in the end up at z? I will just write it down. So this is, it's given as xt of the indicator function at final time. It's not exactly, but it's approximately, I guess, with a proportionality constant and maybe error function instead of exponential, but in some limit. You will see what I mean. Z minus x squared divided by t over t. There's 2 epsilon. So this is again saying, because everything is Gaussian, if I start somewhere, the probability of at the end hitting z scales like an exponential, where like a Gaussian curve, where the difference matters as a square, and that's the expected width that I have to my disposal, linear in time, linear in epsilon. So that sounds realistic. The actual answer, of course, will be an integral, and therefore again like a cumulative error function and so on. But that's a good approximation if it's unlikely, right? So this is not exactly the optimal drift, but this is like an approximation. So if I have that, then I can compute u star minus square root of epsilon. This is just a d by dx, of course. Log psi. So log just gets rid of the x. The derivative gives me a z minus x. The 2 cancels this 2. So in total, I get a 1 over epsilon that cancels the square root epsilon. So this is to the -1. Z minus x over t minus t. So that's u star. From this, we can compute the c, which is, c of xt. It's not the optimal tilt, but the resulting drift for the SD that I should integrate instead of the Brownian motion, which was b of xt minus square root epsilon u star. B is 0, and u star is this thing, so the epsilons cancel. So this is just z minus x over t minus t. This minus cancels this minus. So there might be a sign mistake somewhere here, but first, this is an approximation anyway. But something like that is a good drift, a near optimal drift, excluding events that hit higher than z, because I replaced the integral with only the tail station. So just to let this sink in a bit, what I'm saying is that instead of integrating the Brownian motion, what I actually should do is the following. I should integrate dy is something like z minus yt over t minus t, that's the c, dt plus square root of epsilon dt. I should integrate this process instead. And then consider the important sampling estimator, which in this case looks like m independent realizations of this process. I measure whether or not I hit my extreme event at final time, but multiply it with this change of measure factor that I had before. So the u, just inserting everything back, this concrete c, this scales like 1 over square root of epsilon, integral from 0 to t of the z minus yt over t minus t dwt minus, so I brought it to the other side. This is where the signs change. Maybe you can look at this in your notes if you're interested in every single detail. But something like that. And then z minus yt over t minus t squared dt. So instead of taking Brownian motion, which I call naive here, integrate this SDE instead. Instead of looking at which events exceeded the threshold z and counting them as 1 and the others as 0, still do the same, but do not count the ones at 1, but instead count them with this factor. So this is the factor that we need to integrate up, but we can do that. This is the last thing that I want to attempt doing. So let me first show what it means to integrate this changed differential equation. If the projector becomes noisy again, you just have to live with it, because I guess that's just not solvable. So I call this maybe the importance sampling, maybe importance. I have a function c that is z minus x, so I still call it x so that I can use the same function, over t minus t, what's t? T is nt times dt. So this is just like a lambda function. It's a function of x and t, and I can insert x and t. And then instead of just doing Brownian motion, I need to additionally have xt times dt. This is just the forward Euler integrator. So what's t? T is s times delta t, right? So s is just step, so s times delta t will be t. Maybe that should work already. I mean, I didn't implement the estimator, so this one is incorrect. But you can try it. Importance. How do the XS's look like? And here's what comes out. This is 1,000 realizations of this process. All of them start at 0, but all of them end at z. Z is equal to 10. I guess I can change it. Make z equal to 8. Or maybe minus 8. Why not? Now all of them go to minus 8. The only problem with that, I played around with this, of course, this morning, is that this optimal or near optimal bias is a bit broken. At the last step, lowercase t will be uppercase t. I divide by 0. So the last step has like an infinite push towards z equals x. So numerically, this is a bit broken because I need to temporarily discretize everything. The final point will probably be infinite, yes, so either plus or minus infinite. So actually, it looks like it ends up at the right point. But for the last step, it would need an infinite push towards the correct final point. This I cannot easily discretize, right? So you could do stuff with, like, if I fudge it a bit, this would be even less. Maybe if I add a dt here, I guess that would still work. But now the final points are close to minus 8, but they're not exactly minus 8, right? So if I look at that. Crucially, though, I wouldn't have needed to do any of this stuff on the board. Always nice to say that. I could have used any good guess. Maybe I just want to, on average, push it upwards because the final result I want to be maybe 10 again. So maybe I want to have this be just z over t, implying that this is an average push that at the end, at time t, I would roughly be at z. How does it look like then? So these are now all pushed upwards. They're not like focusing neatly on the endpoint. This is still a random process that maybe averages around 10 now instead of averaging around 0. Yeah. So this was only half the game though, because now we have this other process, but we want to still compute the correct average. So what I need to do is to integrate up this weighting factor. So I want to do this only approximate, which is why it probably will not work optimally, but something according to the following. So the weight is just 1 at the beginning. So maybe 0 times x plus 1. So that's a
vector of the size of x. And then each time step, I say the weight needs to be multiplied with an exponential, right? I'm just saying the time integral I approximate with the sum, and an exponential, and then the sum and the exponent is the same as a product of exponentials. So I'm just integrating the dt components of each of these things. So it will be 1 over square root of epsilon times c, maybe I get the c. C is c of xt. And I need the dw. So I need the dw that I actually take. Square root of dt times the normally distributed one. So that I can then here say this is square root of epsilon times w. Reads nicer anyway. So this is the one step of the dw integral, where c is given from the above. And then I need minus 0.5 divided by epsilon times c squared times dt. Something like that. There might be sign mistakes in here. Let me compare with my notes. Yeah. So I think there must be a minus here. At least that's what I have in my notes, but maybe we'll test both. That's a good thing about it. So this is the weight that I need to add up. And then instead of saying Pz is just this, Pz is supposed to be, this is the indicator function, and then I need to multiply them all with their weight. So let's see whether that makes any sense. What did I do? It's not C, it's CC. This is the variable, yeah, that's the function. Yeah. So these are vectors, so I need to dot multiply them in Math, but Python this would be slightly different. It's a bit much output, so I suppress the dot. And here you see, so the exact result was 7, and my Pz was close. So if I repeat the experiment, I always get these. And to remind you how the paths look like, they are of this form. They're not doing the original thing. They are doing the biased thing. But the weighting factor that I integrated up, which is exactly this Gezanov theorem factor that I integrate over time, at least approximately numerically, gives me the correction factor to the indicator function to reweight it to the original measure that I wanted to get. So now we can go ahead and say, okay, 0.7, that's amateur's work, right? 0.05, right? The actual probability of that is 10 to the minus 6. And we estimate it quite well with just 1,000 samples, 0.01. 10 to the minus 24, right? We would need 10 to the 24 samples to get one of them in the original sampler, the linear sampler. Here we get the right order of magnitude immediately. We probably wouldn't need 1,000 samples. And note that I didn't use the optimal tilt, right? I used this very naive guess. Doesn't even include x and t, right? It's just like, I mean, okay, it's a simple process. But you get the drift, right? I mean, if this would be some more complicated SDE, but you would know what it should do, you could bias it in this form, and you get nice results. I mean, you get a good estimate of these extremely rare probabilities. We can also change z, maybe to 20 or so. I think it should still work. So this is a 10 to the minus 10 event. And the biased trajectories now go on average to 20 just because I biased like that. Of course, this is a very simple SDE. I mean, it's the simplest SDE because it's the one that doesn't have any bias at all. And we know everything exactly. But I didn't use the knowledge of the optimal bias. I just used a good estimator of the bias. It will, of course, go wrong if I don't do it correctly. I don't know. What should we try? Maybe a tenth of that. Then they won't do what I want, right? So this estimator, if you look at the thing, doesn't do what I want. it goes up slightly, but much too little, so that I don't hit the extreme event in the end. So I still end up not measuring any of it. So this P of Z will be broken. But if you do it right, so that you have a good coverage of the ray event that you are trying to estimate, this gives you a much better estimate. So maybe just to be fair to compare to the original one, I think 0.1, 0.1, and 10 was what we used for the naive one. So how did I call the relative error, right? So this is the importance sampling relative error. Instead of doing the naive, I do the importance. Did I call it PZ? I guess so, right? So IS relative error should do 100 times the importance sampling thing. PZ. To check. Why are they not focused on 10? They are not, right? So if I do the importance, now they are. Not doing the right one. ES relative error calls importance, and importance is this one. Somebody get what I'm doing incorrect? So this function is supposed to do 100 experiments. Ah, I have changed the wrong one. And the relative error, so the large number that we had here of the relative error was for the naive one. I just did save it into the wrong file. While now the relative error is 0.06. So our variance is much, much lower than it was before. So this is the importance sampling relative error. And even if I go to a very unlikely event, so we had maybe 20, I think the importance sampling relative error should stay low. Maybe it grows slightly, but it's still all right. It's 8%, right? And this is an event that we would never observe, because what was the exact for this one? 10 to the minus 10, right? We would have never observed in the original. Now we have built an estimator that has a relative error of 8%. So a variance that's 8% of 10 to the minus 10. That's the variance that we had. All right, so this is the short thing that I wanted to discuss at the end, and maybe we will stop here soon. I understand that what I wrote on the board at in the last half hour is maybe of I guess, a bit of a different level than what we did before, but I wanted to do it because SDEs are the thing to go for any kind of complex system. And here is how you change from one SDE to another SDE. You can, in principle, apply this as a blind recipe, right? You do need to know what you're doing in terms of the stochastic integral, but it is still a 20-line MATLAB script, right? And we could easily generalize this to a higher dimensional, not as trivial SDE. It still gets more. So with this, I thank you for your attention again.